All right, here we are in section 3. We want to talk about the properties of amines. Amines are of the geometry or molecular geometry of trigonal pyramid. Okay, so what that means is that if we have trimethylamine, it's shaped like a pyramid, okay, with 3 little legs coming down and a lone pair coming up here, okay? So it's sp3 hybridized, so this would be the sp3 hybrid orbital, okay? And I just want to make note to the back lobe here. That's the back lobe of the hybrid orbital, okay? And it's possible for the electrons to move down into that section and fill it and invert this structure, okay? So this can kind of flip backwards and forwards like a butterfly almost, okay? To make this other guy here. And this happens very fast, so that's why simple amines like this aren't going to be chiral, okay? Now, if you protonate one of these amines, then you lock it in place because there's going to be a hydrogen there, and that can't like fluctuate around, okay? So let's talk about boiling points. Now, boiling points of compounds is always going to be dominated by the intermolecular forces exhibited by that compound, okay? Which means you want to look for the 3 main things and go in order. The first factor is always going to be hydrogen bonding, okay? Hydrogen bonding. The second factor is going to be polarity, okay? And the third factor is going to be surface area, which relates to the London dispersion forces. Okay? So when we look at compounds like this, so extremely briefly, for hydrogen bonding, there's going to be 2 requirements. First requirement is that you need a nitrogen or an oxygen with a lone pair. The second requirement is that you need to have an OH bond or an NH bond. Since, of course, we are dealing with amines, you probably want to be looking for a lone pair on nitrogen and an NH bond, okay? So first molecule has a nitrogen lone pair and it has 2 NH bonds. It has more hydrogen bonding, so it's going to have the highest boiling point. Okay, it has the highest boiling point of this whole series because it has more NH bonds, which can do more hydrogen bonding, which is a sticky interaction that holds molecules together. This guy in the middle here has a nitrogen lone pair and it has an NH, so it also has hydrogen bonding, okay? But not as much as methylamine. This third molecule on the right is trimethylamine. Yes, it does have a lone pair on nitrogens, but in the Lewis structure of that compound, it does not have a hydrogen covalently bonded to a nitrogen, so it has no hydrogen bonding. This is going to have the lowest boiling point. It's probably going to be a gas at room temperature, okay? So that's something to think about there, okay? When we look at, yeah, so we have some values in the textbook here. This has a boiling point of 3 degrees Celsius, so at room temperature it's just going to be a gas. Yeah. So if you have a, and then surface area can be illustrated in the following way. If we have an amine that looks like this, okay, maybe like this, maybe like this, okay, 2, 3, 4, 4, okay. So this has these are all primary amines. So they're going to have the same degree of hydrogen bonding to a first approximation, okay? So they all have the same amount of hydrogen bonding. So let's move to the second criteria, which is polarity. They all have a polar carbon-nitrogen bond, so there's essentially no difference in polarity of these three compounds that I have here. The third difference is to look for surface area. This molecule right here has a very long alkyl group. It's the longest of the three. This has the longest chain, the highest surface area, the highest van der Waals, the highest London dispersion forces, so it's going to have the highest boiling point, okay? This guy over here has 4-carbon chain. This guy over here has a 4-carbon chain. So are they equal? No, it turns out they're different. This is a straight chain, and a straight chain like this pencil that I'm holding up has the greatest amount of surface area so that it can interact with other molecules nearby. So this is going to have the medium, boiling point of the trend. Now, the molecule on the right has 4 carbons that are branched, so it'd be like a crumpled up pencil or a piece of paper. It has less surface area because it's branched, okay? So branched alkyl chains are going to create less surface area because they're more compact, and therefore they're going to have a lower boiling point. For these 3 molecules, this is going to be the lowest boiling point, okay? So that's the basics of it. That's a crash course lesson of chapter 1 or chapter 2 in the textbook in application to amines. Problem 4, it looks kind of complicated, doesn't it? But count your carbons, okay, to see what we're looking at here, okay? This has a total of 6 carbons, this has a total of 6 carbons, and this has a total of 6 carbons, okay? So they all have the same molecular formula. They're all going to have the same kind of mass, molar mass. Now, let's look, again, you want to work through the criteria, okay? The first criteria is hydrogen bonding. That has the greatest influence on boiling points, okay? This is a primary amine, a secondary amine, this is a primary amine, and this is a tertiary amine. Again, we're counting carbons to figure that out. This has 1 NH bond, okay? This has 2 NH bonds. This has 0 NH bonds, okay? So we want to basically look at the difference in hydrogen bonding and predict which is going to have the lowest boiling point. So this is going to have the lowest boiling point. This is going to have the highest boiling point, okay? And this one's going to be intermediate. It's going to have the medium boiling point, okay? Now, what about this methyl hanging off, and the 6-membered ring is not the same as the 5-membered ring? Well, the surface area of a 6-membered ring versus a 5-membered ring is so minor in comparison to the vast difference in hydrogen bonding, which is going to greatly influence the boiling point of these substances, okay? So remember to go down that list. Always look for hydrogen bonding first, make your call. If they're all equal, then look for polarity, okay? And then if they're all approximately equal, last-ditch effort is to look at surface area, okay? So we solved this problem by looking at hydrogen bond. Problem 5, same situation. We want to count carbons. We want to look at things, okay? So this is a primary amine with some other junk on it, okay? So we're looking at the same compound with differences maybe in the alkyl group or something like that, okay? So the first thing you want to do is look at hydrogen bonding, okay? You want to basically count the NH bonds and make sure there's a lone pair on the nitrogens, okay? This has 2 NH bonds. This has 2 NH bonds in the molecule, okay? And this one here has 4 NH bonds, okay? Since it has more NH bonds and an additional nitrogen with a lone pair, it can do twice the amount of hydrogen bonding, right? So molecule C is going to have the highest boiling point. This problem says water solubility, okay? So it's going to be more hydrogen bonding with water, which is hydrogen bonding, so it's going to be most water soluble. Okay? The idea here from hydrogen bonding and polarity, right? If you have more hydrogen bonding, if you have a more polar molecule, it's going to be more water soluble, okay? So that's a crash course review of chapter 2 in the book. So molecule C is the most soluble. Now what about these other 2 molecules, okay? We want to count the grease. Yes, we have this NH2, which is a polar solubilizing group, but we want to count the carbons. This group here has 3 carbons, and this one here has, what, 8, if I'm doing the math correctly, okay? So 8 carbons is much more hydrophobic, it's much more greasy, it's going to dominate the overall characteristics of this molecule. So A is going to be the least water soluble, okay? It's not going to be water soluble. We talked about alcohols back in the alcohol chapter, and we said alcohols that have fewer than 5 carbons are going to be water soluble. So why is that? Well, it doesn't have as much grease. The dominating characteristic is this polar NH2 group that can hydrogen bond with the water, and those 3 carbons, yes, they're greasy, but they don't dominate the overall characteristics of the molecule enough, so this would be expected to be water soluble, okay? And I'm going to say it's intermediate, okay? Intermediate water solubility. Okay. All right. Now let's talk about the basicity of amines. Okay. Now, my job here is to show you a couple things, give you the cliff notes of things, and you might not just understand the depth and the rigor of all the rationale behind it, but you can go to the textbook and read very thorough explanations as to why are tertiary amines more basic than primary amines. But I'm just going to give you the cliff notes here, okay? So first, you should understand the acid-base reactions. So if we have a tertiary amine like this, and we react this with a carboxylic acid, we can make the conjugate acid and the conjugate base on the right. Okay? And so first, you should know how to label the base. The amine is your base, okay? This is acetic acid, that's the acid. On the right, we have the conjugate acid and the conjugate base. Remember that always the acid forms the conjugate base and the base forms the conjugate acid, okay? So it's the flip side of the reaction. To figure out the direction of equilibrium, you need to label the pKa's on each side. So here's our acid. We want to label the pKa of acetic acid. This is 4.76. I normally say about 5. I round everything off to 5, 10, 15, 20 or something, okay? The pKa of an ammonium like this guy here on the right is about 10. It's actually, I don't have the exact number for this. It'd be more like 11 or something, but I'm going to say it's approximately equal to 10, okay? Now, to figure out the direction of equilibrium, you look at the lower pKa, okay? That means it's more acidic. And if something's more acidic, think about the left acid and the right acid fighting, okay? The left acid is more acidic, so it's going to push to the right. It pushes away from that. So we draw the equilibrium arrow showing to the right. The equilibrium for this reaction is going to be greater than 1, okay? You have different pKa table on table 23.1. Okay, and let me just verbally say what we have here. Methylamine, ethylamine, isopropylamine, cyclohexylamine, we have a pKa of 10.6, 10.6, 10.6, 10.7. So guess what I'm going to say? I'm going to say the pKa of a protonated primary amine is about 10, okay? On the right, You have dimethylamine, diethylamine, trimethylamine, and triethylamine. And the pKa's for those are 10.7, 10, 11, 9.6, and 10.8. So it's about 10, okay? So if you have 2 R groups, if you have 3 R groups, okay, the pKa for all of these is about 10, okay? Now, this is where things get a little bit different when you talk about anilines, okay? So your alkyl amines have a conjugate acid of about 10. That's a good round number to remember, okay? You don't need to memorize this one's 10.6 and this one's 10.7. That's not critical. About 10, all right? And so if we look at table 23.2, we look at aryl amines and heterocyclic amines. So let's talk about aryl amines first, okay? And here, of course, we're talking about aniline, okay? Aniline we have methyl aniline, we have NN-dimethyl aniline, okay? And the pKa for those are 4.6, 4.8, 5.1. So what I like to do, again, is round this off to a nice whole round number, pKa 5. What does that mean? Well, a lower pKa means more acidic. Oh, I should draw in the actual protonated forms of the, let me carefully do that, okay? So we're talking about the conjugate base, all right? So aniline, when it becomes protonated, okay, has a pKa of 5. These guys are really acidic. pKa 5 is much lower than pKa 10, so it's much more acidic. And the question is, why? Why are these guys so much more acidic? The reason why is because the base is super stabilized, okay? Let me explain why on the next slide. Okay. This pKa is about 5, okay? It's very acidic, much like acetic acid, which we memorized to a round number is about 5 as well, okay? So this has the acidity of acetic acid. It's like really acidic. Why? Why is it acidic? When it loses a proton, you form aniline, okay? And the reason why it's so acidic is because the conjugate base is resonance stabilized. Okay? Let me emphasize that by saying the lone pair that's produced is spread out, okay? Remember, whenever electrons can spread out over a molecule, it creates a very stable situation. So these lone pairs here, okay, can engage in conjugation with the pi bonding electrons in the aromatic ring to give you various resonance structures, okay? Let's draw them out. The negative charge could exist at the para position. Negative charge could exist at the ortho position. And we could take this back up to the top, okay? So whenever you have lone pairs and an amine that are resonance delocalized, that makes the conjugate base side of the equation so much more stable, and the equilibrium constant is going to lie towards the right, which means the acid is less stable, or it's more acidic, or it has a lower pKa. If you look at this guy here, okay, and this guy here, let's say we deprotonate this pKa is about 10, and this one's like, you know, not very acidic. What we get is this amine where the nitrogen atom is localized, okay? The lone pair is localized as opposed to delocalized. And remember again, it's that little sp3 hybrid orbital. You're making those two electrons stay in one little one-bedroom apartment, and they're going to be fighting each other. But in this case with aniline, they have this huge apartment building. It's vacant. They're just running around and they're spread out, and it's a quite stable situation, okay? So this is the reason why anilines are so much more acidic than normal amines. Of course, we're always talking about the conjugate acid, okay? The conjugate acid. Heterocyclic amines, okay, are going to be extremely acidic here's the caveat, when you form an aromatic ring. Okay, so example number 1, let's take pyrrole. This guy here is not aromatic. It's not completely conjugated, which means we don't have a p orbital on every atom because that nitrogen is sp3 hybridized. Okay, it's sp3 hybridized. There's no lone pair on that nitrogen. We don't have 4n plus 2. We don't have the 6 electrons here. Okay, it's not cyclic. It's not completely conjugated. If we lose a proton, okay, we can say a lot of things about those lone pairs, but these lone pairs are magical. They're part of the 4n plus 2. So it's not just resonance. It's like a Superman resonance. And so the pKa here is about 0. Okay? It says 0.4 in the book, but this is 0. So that's 5 orders of magnitude more acidic than aniline. Okay? And so this guy is aromatic. If the molecule reacts as an acid to form something that's aromatic, it's gone. Okay? That's going to be very favorable. Now, why is pyridine not so acidic? So here's protonated pyridinium, okay? And when we form pyridine, okay, this guy here has a pKa of about 5. It's 5.3, okay? So why is it not too acidic? Why? Well, this guy here has 4n plus 2. It's aromatic. This guy on the right has 4n plus 2. Again, we're just counting these electrons here. This is 4n plus 2 as well. This is aromatic. Okay? And let's review a little bit about aromaticity and hybridization and stuff like this. When you have a nitrogen as part of a aromatic ring and it has the pi bond on it, that's your p orbital that's already used to make the pi bond. Those lone pairs are not in a p orbital. It can't make a second pi bond. So those lone pairs are not in the ring. They're twisted orthogonal. They're in the plane of the board here, and they're in an sp2 hybrid orbital. So that's an sp2 hybridized lone pair. So you're not restoring aromaticity, and that's why the pKa of pyridine is not too good, okay? And so we use pyridine as a base, okay? It's a suitable base, just like triethylamine would be a suitable base, okay? Now let's talk about substituted anilines. Okay, substituted anilines. So again, remember again that this is aniline. And when it reacts with H+, it can protonate the amine, okay? All right, and we said that the pKa here was about 5, okay? 5, nice round whole number, okay? And that's for aniline. And we talked about why it would favor the molecules on the left, because the aniline is resonance stabilized. Okay. Another way of thinking about it is that this structure is angry because the positive charge is just localized just on that nitrogen. It's not spread out, okay? We can't move the positive charge around the ring, okay? We can't delocalize the positive charge. Now, when we have anilines, okay, like such, we want to think, how else can we stabilize the lone pairs? If you can answer this question, you've got this section made in the textbook, okay? So we already know that we can stabilize the lone pair on nitrogen by an adjacent phenyl ring because of all the resonance structures that stabilize that lone pair. But think about how else you can stabilize lone pairs. You can stabilize that with electron withdrawing groups in the ortho-para direction. So you can add electron withdrawing groups. Specifically at the ortho and para direction positions. Why ortho-para? Let's go back to our resonance structures here that I drew regarding aniline. Here's the orthocarbon with a negative charge. Here's the orthocarbon with a negative charge. Para carbon with a negative charge. And here's an orthocarbon with a negative charge. So if we place groups at the ortho and para position, right where that negative charge would be, and they're electron withdrawing, they'll accept those electrons and help stabilize the structure even further. Okay? So that's what you want to think about. So the textbook lists various things like chlorine, nitrile, and nitro groups. Okay? Chlorine is an electron withdrawing group. Okay? The nitrile group is an electron withdrawing group, and the nitro group is one of the best electron withdrawing groups you can possibly have. Okay? So if we position a nitro group at the para position or a nitro group at the ortho position, that's going to make the acidity dramatically different. Okay? For example, para-nitroaniline has a pKa of 1.0. Okay? So it's dropped. It's more acidic. Okay? Point number 2 is that if you have electron donating groups at the on the ring, it's going to destabilize the lone pair. So it's going to make it less acidic. What's an electron donating group? An NH2 group, a methoxy group, a methyl group are illustrated in the table. So NH2 is an electron donating group because of the lone pairs. Okay? Methoxy is an electron donating group because of the lone pairs. A methyl group is an electron donating group because of the slight inductive effect. Okay? So that's going to make it less acidic, all right? So again, cliff notes, broad strokes. You'll need to read a little bit more about that if you like. Let's go ahead and make one last comment before we do some practice problems, okay? If we have an amine, that's more acidic it's going to create a base that's less basic. Okay? This might sound foreign to you, so let me give you a general chemistry example that we definitely know about. HCl is very acidic. We know it's a strong acid. Okay? No doubt about that. And what we form is chloride and H+. Chloride is neutral. It's not basic. Okay? So this is very acidic, and chloride would be like not a base at all. Okay, so that's what I mean by less basic. It's so little of a base that it's not a base in this case. Okay, now let's discuss acetic acid. Okay, acetic acid is a weak base. It's less acidic, which means that the basic form is going to be more basic. Okay, so less on one side means more on the other. Okay, so we're going to see problems that say which of the following amines is more basic. Okay, and we can think about it in terms of just the structure, okay, whether you have aniline or whether it's a primary, a secondary, a tertiary amine, or you can think about it in terms of the acid. So stick an H on there, put a plus on the nitrogen, and then think about, okay, how acidic is that conjugate acid? Think about it, and then if it's really, really acidic, then we would say, well, that amine is not very basic. Okay, you get the opposite result. Okay, so you can think about the acid and then reverse your thinking and say it's less basic, or think about the acid and say it's less basic, reverse your thinking, and then say the amine is more basic. Okay, so it's always going to be more or less or more. Okay, so strong acids are not going to have very strong bases as their conjugate base. In this problem, we're asked to figure out which of the two compounds is the stronger base. So a stronger base is going to have an unhappy lone pair nitrogen. So the nitrogen lone pair is unhappy. All right, so let me look at that and you'll see what I mean by this. Okay, this lone pair is localized, it's high energy. Okay, the lone pair on the right is conjugated, it's next to the pi bond, it's hooked up. All right, so that's delocalized. Localized means high energy, reactive, basic. Delocalized means low energy, stabilized, less basic. So, final answer. The stronger base is going to be the one on the left. Okay. Part B. Let's look at some things here. Okay. So this nitrogen has a lone pair. This nitrogen has a lone pair. Let's count the total pi bonding electrons in this aromatic or anti-aromatic system. So we've got 2, 4, 6. 6 electrons is 4 times 1 plus 2. So that satisfies the 4n plus 2 rule. This is aromatic. And this lone pair is super, super happy, okay? We're going to call this molecule stable. It's not too good to call molecules happy. So this is very stable. It's not basic. Okay? Over here on the right, we've got 2, 4, 6, 8 electrons. 8 electrons is 4 times 2. That satisfies the 4n rule. We're going to call this anti-aromatic. That's extremely unstable. This means that this compound is going to react in any way possible to get rid of that situation. For example, reacting with an acid. So this is going to be very, very basic, okay? Final answer, molecule on the right. Okay? There's a lot of logic here, and I'm not writing it all down, but I'm verbalizing it. So please take notes if you're trying to remember this and learn this, okay? Part C, this is a great problem. So we have a lone pair on this nitrogen. There's no resonance structures we can draw for this. We're going to call this localized. We're going to say this is going to be more basic. Molecule on the right is not an amine, it's an amide. This nitrogen lone pair is resonance stabilized via this electronegative oxygen with the pi bond, okay? So we're going to call this delocalized, meaning that lone pair is very stable. It's engaged with the oxygen. It's not really available as a basic lone pair to attack an acid. So we're going to say this is less basic. Final answer, molecule on the left. Let's look at molecule part D. So we've got a lone pair here and a lone pair here. Let's go ahead and count the pi bonding electrons and highlight them as well, okay? So this one has 2, 4, 6, 8. There's no pi bonds going to this nitrogen, so we count this lone pair here, okay? So 2, 4, 6, 8, 10. 10 electrons is 4 times 2 plus 2. That satisfies the 4n plus 2 rule, okay? Yeah, my math is correct there. Okay, so we say that this is aromatic. It's stable. It's not basic. This molecule on the right, let's count the pi bonds, okay? We got 2, 4, 6, 8. Which electrons do we count? Well, we count the pi bond, which is going to the nitrogen. Since there's a pi bond to the nitrogen, we don't count those lone pairs that I've highlighted in purple there, okay? So this has 2, 4, 6, 8, 10. 10 electrons is also aromatic. Okay? So wait a minute, do we say it's not basic? Well, those lone pairs are in purple, so it's like a completely different lone pair, not part of the aromatic ring that's available, okay? So the electrons I've highlighted in light blue here are all involved with the aromatic ring. These ones that I'm pointing an arrow to are involved in the aromatic ring, and since they're involved with the 4n plus 2, they have to stay there, okay? They have to be part of the aromatic ring. However, let's look at this purple arrow. This purple arrow is pointing to the lone pairs there. It's not part of the 4n plus 2, so that's a straggler. That's a person sitting on the bench of the game, and that person's available to run, get a drink of water, or act as a base. Okay, so this is going to be the more basic lone pair. And we talked about pyridine before, so this should all be making sense. So that's going to be the more basic compound. Okay? Number 7, rank the following compounds in terms of increasing basicity. So again, we're examining the lone pairs on the nitrogen atom and how their resonance delocalized, okay? So there seems to be a difference between these 3 compounds at the para position of the 2 flanking phenyl rings, okay? We have a hydrogen and we have a hydrogen. A hydrogen is not considered an electron withdrawing group nor an electron donating group. So it's in the middle, it's neutral, okay? Methyl groups, remember again, are slight electron donating groups. Okay? And bromine is an electron withdrawing group, and things with pi bonds, right, adjacent at the benzylic carbon, are strong electron withdrawing groups, okay? So this has 2 electron withdrawing groups, this has 2 electron donating groups, and this one's in between. So we can already say that this molecule here is in between, okay? Now remember what I told you, electron withdrawing groups stabilize the lone pair, make it more stable and just like lethargic. It's on the couch, it's got 3 cell phones, and it's texting all of its friends. This person or molecule is texting all of its other friend molecules. And that is very busy, okay? So this is a busy lone pair that's engaged with a lot of aromatic rings and even this electron withdrawing group and influenced by this electron withdrawing group. So this lone pair is very stable, okay? Not acidic. Okay, least acidic. Okay, and again, we think about electron donating groups as in the analogy I gave in the aromatic chapter. These are siblings that are saying, get off your butt, get off the couch, you know, go vacuum do your laundry, you know, put away this. It's all cluttered on the hallway. You know, you can't even walk down the hallway. So these electron donating groups anger the lone pair. They're pushing electrons towards the nitrogen, which already has lone pair electrons. So that lone pair is like, I'm out of here. I'm going to get in my car and go to my friend's house, okay? So this is very basic. Okay? So, I meant to say basic over here. So this is very basic. This is not basic. Well, the least basic. And this is in between, okay? I think you should read the book, and the wording in the book might be there so you could reread and very slowly analyze things and get the feel for things. But this is just the cliff notes for this section. Thanks for watching, and we'll get started with the next part.